In this work, in collaboration with Toshiba Europe and the University of Cambridge, we present a dataset as a tool for testing photometric stereo methods using point light sources in the near field. The motivation behind this work is the lack of a shared data across the computer vision community that prevented methods for reconstructing 3D shapes with photometric stereo data to be fairly evaluated. Although far-field photometric stereo datasets already exist, when it comes to evaluate methods that are supposed to interpret 3D geometry at per pixel level using light emitted from a point light sources, such as LEDs, the proximity between the camera light system and the object is crucial. Nonlinear light propagation and attenuation, but also self-reflection and shadows, become far from being negligible. Our dataset consists of 14 objects made of heterogeneous materials. The photometric stereo data have been acquired placing the objects at a variable distance which depends on the size of them, varying between 10 to 30 centimeters from the camera light system. The capturing setup consists of a FLIR RGB camera with 8mm lens, 52 bright LEDs with a global voltage regulator, and a microcontroller to synchronize them with the camera itself. The light calibration procedure follows an isotropic point light source model. For every source, it assumes a known position in the 3D space, a principal direction, and an angular dissipation factor. To estimate these factors during the light calibration, we firstly measure the LED brightness with a lux meter to have an initial guess in terms of brightness. After that, we use a purely Lambertian plane placed at several distances to estimate all the parameters. The acquisition of the ground truth meshes has been done using a structured light GOM ATO scanner. No spray coating has been used, however, for some objects, markers have been used and segmented out in the mask provided in the dataset. Mesh alignment from the GOM scanner and the registration with the photometric stereo images have been done using MeshLab. Instead, the normal maps have been rendered with Blender. Using this dataset, we perform an extensive evaluation of the latest near-field photometric stereo approaches in order to provide a fair quantitative comparison. To emphasize the need of tackling near-field effect properly, we also compare with the method proposed by Ikehata, which addressed far-field assumption, therefore it performs worse than the others. As recent research trends on 3D reconstruction using photometric stereo have shown an increasing interest to deal under near-field lighting conditions, we hope these datasets can provide a fair platform in order to evaluate newest methods in these settings.